Okay, welcome everyone to the virtual time series seminar. We are very happy today to have Marie-Christine Düker and Younghoon Kim presenting with this paper on testing for common structures in high-dimensional factor models. Marie, the floor is yours.
Yeah, thank you for the introduction, and also thank you for inviting me and giving me the opportunity to talk here. So I'm going to talk about a project which is based on a joint work with Vladas Pipilas, who is at the University of North Carolina. And my guest panelist is Younghoon Kim, who is a postdoc at Cornell University with Shumante Basu. And he's one of Vladas's former students. So he's doing a lot of work on high-dimensional time series, in particular factor models and multi-subject learning, which is also going to be part of this talk. So there's, I think, a close connection between our research. With that, I'm going to start with the content. So I'm going to give at first some motivation for our test. So why are we even looking at those common structures? And then I will introduce the testing procedure and give some motivation of how we construct this test. And later on, introduce the test statistic, answer some related questions, and finally get to some data example. So yeah, I guess for this kind of audience, I think everyone is more or less familiar with factor models, but just to also kind of settle on our notation, I'm going to start from the beginning. So the idea is that we go look at high-dimensional time series. So we observe a vector at each time point t. So we assume that this vector is d-dimensional, but we definitely have in mind that d might be large, even larger than our sample size t. So, and usually in high-dimensional statistics, we make some kind of assumption on a lower dimensional structure. And in the factor model setting, we kind of suppose that our data are driven by a relatively small number of latent time series. And it is kind of assumed that the dependence in the data can be attributed to the small number of common factors. So, and the co-movements of the observed time series are basically assumed to be driven by those dynamic structures. And we will use the following notation. So we have our xt, and then we have our factors, which are r-dimensional. So r is assumed to be small. And we have our errors epsilon t, and then the most important part, our factors, which actually push the lower dimensional structure, the factors to the higher dimensional space, RD. So a typical assumption would be to just assume that the FT follow a vector autoregression model of order P maybe. And the question of interest we are going to ask is basically coming from two different directions. So one is from change point analysis, and the other direction is multitask learning. So this multitask learning term is often used in machine learning or in a machine learning context. And the question people asked in the change point setting is, okay, can we really assume that lambda stays the same over time, or does this loading matrix change? And in multitask learning, one kind of pushes it to the setting where one observes multiple data sets and assumes that those can be modeled through factor models, and then asks the question of whether those models share the same loading matrix. So, but we're going to go into a little bit more detail on that. So first of all, the change point setting, again, we have our multivariate time series. And now we are saying, well, for the time points before some t0, we model it through some lambda 1. And then for the time points after t0, we model it through some lambda 2. So we allow for those lambdas pre and post t0 to be different. So the hypothesis people have been looking at is then, okay, lambda 1 and lambda 2 are equal. So, and this kind of hypothesis is a very popular problem in the economics literature. So, I mean, there has been a ton of literature on this question. And what people usually look at is they consider this kind of hypothesis, but then they also discuss the possible alternatives. So, and the possible alternatives are usually three different kinds of alternatives or three different types. So the first one is that lambda 1 and lambda 2 are linearly independent. So there's no relationship or common structure between the columns. So the second one is that some, but not all of the columns are linearly independent. And the third one is a little bit stronger, where we even say that there might be some kind of rotational change. So there's still a lot of similarity between the loadings because they only differ by some linear transformation given through some matrix phi. So, and in particular, this is also observationally equivalent to a change in the volatility of the factors, which is again like a lower dimensional object. So this would be like an R times R matrix, and one would kind of say like pre and post break, those two covariance matrices only differ by some transformation, which is given through this matrix phi. And okay, this matrix would then be assumed to be like full rank, right? So yeah, to make some literature review or give some kind of literature review, this kind of question has become like really popular in the last 10 years. So I mean, since this paper by Han and Inouye in 2015, who proposed a QSUM type or also like wall type test statistic to test for changes in the loadings over time. There has been like a lot of literature, people proposing basically different kinds of tests for this kind of setting. So by in 2022, proposed like a likelihood ratio type of test. And then there was like a ton of other literature, which is like similar to this kind of test, but basically answering questions like, okay, what if we have multiple changes, or proposing different approaches based on a wavelet-based test statistic. And the other thing is that people have been like trying to simultaneously estimate time varying loadings and the factors. And there's always the question of like, how do I estimate the number of factors? And people have considered like how the number of factors can also change, and so on and so on. So there's been like a ton of this literature. But the question we are interested in is it actually possible to kind of test for one of those alternatives? Because, okay, people have been like giving those alternatives, but can we actually distinguish between them? And is there something interesting in looking at those alternatives? So this is like kind of one of the directions we are coming from, where one kind of tries to look for differences in the loadings, but a specific type of difference. But the other direction we are coming from is multitask learning. So again, when we look at just like one factor model for a time series for one object, this kind of allows us to study the intra-individual variability. But now we are kind of interested in not just studying that, we kind of also want to study the inter-individual differences and similarities in intra-individual variability when we look at multiple factor models. So this is kind of the task in multi-subject learning, where we want to study those like similarities. And this type of question is popular in a different set of literature. So it comes from a very different direction. People are mostly interested in this kind of question in psychometrics, behavioral sciences, and neuroscience. And you can like already guess why, because this is often like related to having multivariate data sets for multiple individuals. So a good example is, for example, in neuroscience, when we look at fMRI data. So we have time series, basically, which are usually high dimensional. So it kind of depends on how the neuroscientist separates the brain in different regions. So oftentimes the number of regions is like 86 or something, but it depends on the data set. But you definitely get something high dimensional. And then one would be interested in seeing whether there are similarities between individuals when I model those data through a factor model. So I get basically a data set for every individual, and maybe I can even cluster those into groups depending on whether people have some kind of condition, some kind of injury or brain injury, and then based on those similarities make some inference. So this is the other direction we are coming from. We are going to start with just looking at two subjects. So we assume that we have data for two subjects, and we model both of those through a factor model. So again, we allow for different loadings, which already reminds us of the setting in this change point situation. So, and I was already referring to this literature where people look at data for different individuals. And yeah, so people have been studying this, or have studied this kind of setting. But people have mostly been interested in how to do estimation. So those 3 publications are all from the psychometrics literature, and they have studied how to estimate this kind of situation where you have multiple factor models. So here I wrote it in a setting where we have 2 and assume that lambda is the same. And people wanted to basically solve this objective function, but subject to this constraint that the covariances of the factors follow a certain structure. And the structure is given by a mutual covariance matrix sigma. So sigma is the same across individuals, but then those matrices dk are allowed to change from individual to individual. So people have looked into solving this objective function, and oftentimes they assume that the dks are actually diagonal matrices. And again, this kind of problem of interest here is equivalent to having this kind of representation of our loadings. So it could also be considered as a change in the loadings, but a structure change in some way, because we have a similar loading matrix or the same loading matrix lambda, but transformed by some matrix dk, which is allowed to differ from individual to individual. So this way we can kind of reformulate this objective function and have a different constraint, basically. However, what is important here, people have been trying to propose algorithms to solve this objective function, but there is basically no way of telling whether this prior assumption that my data satisfy this is actually true. So, and this is kind of what we wanted to look into. And you can already see that this kind of relationship is very similar to our type 3 break, only that here this matrix is diagonal. But yeah, it kind of resembles our type 3 break from the change point setting. So now we are asking, is it possible to test whether the data actually satisfy this kind of type 3 break? Or in this setting of having 2 individuals, whether those loading matrices satisfy this relationship. Okay, so the idea is to propose a test to test for this type 3 break. So, and just to summarize, our null hypothesis can then be formalized as having that each lambda satisfies this kind of relationship. So we have a mutual lambda, and then we have a matrix phi k, which is allowed to change from individual to individual or over time. So again, we know that the type 3 break has this nice property that it's observationally equivalent to having a change by a non-singular matrix phi, or a transformation by a non-singular matrix phi in the volatility of the factors. So yeah, and again, we are assuming that the phi k are non-singular, so that we have this kind of rotational change. So, and the alternative is that we have that a non-negligible portion of the cross sections have linearly independent loadings. So there's some kind of relationship that those are unequal. So basically this hypothesis is not satisfied. Yeah, just before I move on to the actual test, I give a small example just to give a little bit of intuition for our data. So it's a very, very simple example. So the simplest kind of setting we can get under this hypothesis. So when our transformation phi1 is equal to the identity matrix in this hypothesis, and phi2 is equal to some kind of diagonal matrix, and we assume that we have some joint matrix lambda, then lambda 1 is constructed through lambda, and lambda 2 is constructed through this transformation by a diagonal matrix. And we also assume that our factors have covariance matrix equal to the identity. So, and again, we come back to this fact that it's observationally equivalent to having changes in the second order structure. And that kind of makes it a little bit more interesting, because then we can see, well, the change thus happens on the diagonals. So basically we just know that our factors changed in variance. So just the variance of our factors has changed, the loadings are the same. So, and this can kind of give us a hint that maybe the structural changes are actually more homogeneous, or that there's something more going on. The similarities, there are still similarities between the factors and the loadings. Okay, so coming to the testing procedure. So in order to propose a test for that, let's recall our hypothesis and then think of what this hypothesis actually means. So it just says that the columns of our lambda k lie in a subspace generated by the columns of this joint matrix lambda. So, and then the hypothesis can actually be rephrased through a projection matrix P0. So, and the hypothesis can then be written as a transformation by this projection matrix, and we should still get the same lambda k by applying this projection matrix, because we are kind of using the projection matrix onto the subspace generated by lambda. So, and since lambda has those like linearly independent columns by assumption under the hypothesis, the projection matrix has this very nice form. So then another nice property of the projection matrix is then when I apply a transformation with a non-singular matrix, which is the case under our hypothesis, then we actually see that those projection matrices are invariant under this transformation. And this is something we want to take advantage of. So it means that the projection matrices calculated for both lambda 1 and lambda 2 are actually going to be the same under the hypothesis. So another way of rephrasing this hypothesis would basically be to say P01 is equal to P02. So before we get to the test, just let's recall the estimation. So estimation for factor models is always done through, or one way is to concatenate over time. So this gives us this closed form. So xk would basically be just the concatenated series over time. So we would have t vectors of dimension d concatenated, and then we calculate based on that our covariance or sample covariance matrix. And then we use the first r eigenvectors corresponding to the r largest eigenvalues of sigma for our PCA estimators, and we get an estimator for our factors, and based on that, we can also estimate our loading matrices. So this is just a regular procedure of like how to do estimation, and for now we assume that we know the number of factors. So getting to our testing procedure, the idea is now to transform the data such that the pre and post break loadings are the same under the hypothesis, which is actually not the case, right? So, but this is what the regular change point test does. So, and this is something we want to achieve by transforming our data. So let's recall our projection matrix and then use our PCA estimators to estimate the loading matrices. So, and then we can get estimators for projection matrices based on the first and based on the second series. So we basically get two of those projection matrices. And again, those loadings are based, or the loading estimators are based on our PCA estimates. Okay, so how can we actually transform our data so that we get no change under the hypothesis, but a change under our alternatives? So the idea is, and for now, let's focus on the orange part, that we take one of our two series when we are in the two subject setting and split the data into two halves. So we look at the data 1 to t over 2, and then t over 2 plus 1 to t. And then we transform the data by applying the projection matrix from the other series. So we calculate our estimator of the projection matrix based on our series x1, and we apply this projection matrix to the first part. So, and we don't change the second part for now. So just ignore the black parts here. So, and the motivation for that is that under the null hypothesis, when we go to and look at this at the population level to get some intuition for what's happening, when we transform our series x2 with P01, so again, this is the projection matrix under or at the population level, and apply it to our factors multiplied by this loading matrix lambda2, we can actually see that this projection matrix, which is invariant under transformation with a non-singular matrix, doesn't change anything, right? We still get lambda2. So now getting to this black part here, well, one can see that here P2 doesn't change anything, right? Obviously, because I'm using the projection matrix based on the same loading matrix. Moving on to see what happens under the alternative, and also why we need this like black part of the transformation. Well, the black part we need to ensure that our transformed series still satisfies all the assumptions, we need to apply a regular change point test. So, and the idea is that we need two things. We need that our error terms of the transformed series are still stationary. That is one thing, and that they have positive definite covariances, at least when our original series satisfies that, right? So, and when we do this transformation with P01 and P02, this is not necessarily satisfied that we have positive definite covariances, but when we add this identity, we actually achieve that, because the P0s, they are actually low-ranked matrices. So the stationarity assumption is satisfied because P01 and P02 are actually the same under the hypothesis. So this is why we use this transformation by P hat 2 to the second part of our, so after splitting the series into two halves. So the question is now, what happens when the hypothesis is not satisfied? Well, when the hypothesis is not satisfied, we actually want to have that our transformed series admits a change point at T/2, right? A structural change in the loadings. So, and this is actually the case because when we transform again at the population level with P01, we don't get the same loading matrix anymore, because lambda1 times lambda2 is not the same as lambda1 times lambda1, right? So this doesn't go away. So we don't really end up with the same loading matrix anymore. And this is kind of what we want to take advantage of. So again, now that we have our transformed series, the idea is to apply a regular change point test. So to apply a regular change point test, again, recall our PCA estimates. So we just use our eigenvectors corresponding to the R largest eigenvalues of our sample covariance matrix. And then we apply maybe the most basic test statistic, or the first one people looked at. This is based on the Han and Inouye paper I mentioned earlier, which just compares the pre and the post-sample means of the sample of GT times GT transpose. So we use our estimators of the PCA estimators for the factors of the transformed series to compare pre and post break, while the break is actually a T/2, so T half, because we actually kind of artificially created this change point, right? So we know where the change point happens if it happens. So, and then this is like kind of a regular QSUM type of test statistic. Then Han and Inouye suggest to vectorize that, which means we stack each column underneath each other, but only for the lower, everything below the diagonal. So, and then we can write down our test statistic, which is then a wall type test statistic. We just use an appropriate normalization for the long run variance matrix. So this long run variance matrix can also be estimated based on our factors and gives us a consistent estimator under certain assumptions. And this omega is actually based on some kernel estimator, but I'm not going to go into more detail on that. The important part here is we have this like wall type test statistic, and we can show that this test statistic converges under the hypothesis. So under the hypothesis, we get very much the same result as Han and Inouye. So we can actually show that this wall type test statistic converges to a chi-square distribution where the degrees of freedom depend on the number of factors. So R was the number of factors, so we get that it converges in distribution to a chi-square distribution. And maybe to emphasize here, our assumptions are just on the individual data sets, right? So when we assume we are in this like two subject setting, we make assumptions on those two models, and we assume that both can be modeled through a factor model. And then we impose the regular assumptions we need to do estimation on the individual series. And we can also ensure that we are in a high dimensional setting. So we allow square root of T/D to go to 0, and T and D are as T and D go to infinity. So the dimension and the sample size, which is also the exact same assumptions as in the Han and Inouye paper. Yeah, so from a theoretical point of view, it's really just that we have to have a close look into the proof of Han and Inouye for their test statistic, because we use the exact same idea, and that is that we need to show that our estimators, the PCA estimates for the transformed series, are still consistent estimates. And I wrote a very rough thing here to not go into more of the technical details, but the quintessence of this is basically that we need that the G hats kind of consistently estimate the actual factors. And okay, this is kind of up to its transformation, of course, because okay, those models are not identifiable. And here I wrote G, but what we actually estimate is the true factors of the underlying series, which we transformed, right? Because the transformation is supposed to not change anything about the factors or the loadings, at least under the hypothesis. So, and this is kind of part of the, or the main part of the proof, and then use the similar techniques as in Han and Inouye. So this allows us to get convergence under the hypothesis. But we can also show that under the alternative, this estimator is consistent in the sense that under the alternative, we get that the test statistic diverges. And we get a very similar result as in Han and Inouye by just considering the two other alternatives we looked at the beginning, because at the beginning we showed like there are three different types of alternative. One is the rotational change we are looking at. And then there are the two other ones where we have partial changes in the loadings, or that the loadings are completely linearly independent. And under those assumptions, one can show that the subsample means basically converge to different limits. And by subsample means, I mean those two means. Okay. So, and now there are some questions, I guess, in the sense that one can kind of push this a little bit farther, right? One can like think about, well, what happens if we have different numbers of factors, right? Because for now, we kind of assume we know the number of factors, and it's the same for both individuals or pre and post break. But it turns out that with a little bit of a modification, we can also answer that question. So we suppose that lambda1 and lambda2 actually have different dimensions. So still, okay, sorry, this is supposed to be a D. So we still know that lambda1 and lambda2 are D times R, but R is allowed to be different. So we have R1 and R2, and we assume that lambda1 comes from a factor model with potentially more factors. So, and we assume that this kind of relationship is satisfied. And again, this matrix here has full column rank. And we can actually kind of see that our previous test relied like heavily on having this invariance of the projection matrices under transformation with a non-singular matrix. However, in this case, this is not satisfied anymore because our matrix phi2 is not a square matrix anymore. So we looked into some alternatives to actually still adopt our procedure. And it turned out that it's possible by using a different type of relationship. And this relationship is that the product of the two projection matrices P2 and P1 is actually equal to the projection matrix P2. And this can then lead to a different type of transformation, but the idea is still similar, right? Or still kind of the same. So we are transforming our data pre and post break, and this break is artificially created by this transformation. And we use again the PCA estimates for those projection matrices. Yeah, so before I move on to some other discussion, a little bit on the simulation part. So we kind of conducted very similar simulations as in the Han and Inouye paper, actually. We considered that the dimension and the sample size are both 200 and 500. Here in this case, we looked at the hypothesis, and we are in the two-subject setting. So we have two subjects. We have potentially two different loading matrices. But when we look under the hypothesis, we assume that those loadings are either equal or they undergo some rotational change, so by some non-singular matrix. And then we did a look at like 4 different settings, and one can see that the nominal level of 5% is like almost achieved in all those cases. We looked at four different settings, which I only described very briefly here. So we have like independent factors and errors, and then we allow for temporal correlation in the errors and the factors in the data generating model 2 and 3. And in the last setting, we also allowed for different DGPs, so data generating processes in both subjects. So for each subject, we assumed basically, or we allowed those subjects to be modeled through different models. So one has like correlation in the errors, one has correlation in the factors, for example, and one can see it like still works fine. So we kind of get to the 5% level. I mean, the issues we are seeing are mostly issues which also occur like in the Han and Inouye paper, and subsequently published papers on this topic have tried to kind of address that through proposing different tests and comparing it to the Han and Inouye paper. So also moving on to the alternative, again, we are in this 2-subject analysis. We look at the alternatives, which basically means now there is no rotational change, but there are changes of different kinds. So for example, the first one is an additive change. We again assume that D and T are both either 200 or 500. And what I mean by additive change is that I add basically some kind of constant to the loadings, and then I increase how big this additive change is. And one can see it has problems when the additive change is small, but with increasing this number B, I actually get a good power of the test. And this is also very, very similar to the Han and Inouye results, right? So we also used very similar data generating processes for that. And the second one is also interesting because this is kind of an additive change across a partial set of loadings. So a partial set, by a partial set, I mean, I look at I change 20% of the loading entries, and then I increase it to like 80%, and one can see how the test improves, and also how the test improves with increasing sample size. So, and just to get to the last 2 columns, where we can see that the test has really good power. This actually is a partial change in the loadings plus a rotational change. So what I mean by that, we have a partial change. So some of the columns change, but then some of the columns undergo rotational change. And I basically increase the number of vectors which undergo rotational change. So if I increased it up to 4, I would be under the hypothesis. And here one can also see nicely how the power kind of decreases because we kind of get closer to the hypothesis, which is not the case in the 4th one. Here the power is still good. So just to conclude the simulations, we also talk a little bit about the change point setting, but only under the hypothesis. One is in the same setting again. So we have D and T being 200 and 500. And then we looked at different changes. So the idea in the change point setting is always that we apply a regular change point test first. And when this regular change point test rejects the hypothesis, we move on to applying our test, right? So we find a change point. So the regular test tells us there is a change point at some point, and the loadings undergo some kind of change. And then we want to basically specify what kind of change that is. Can we see whether it's like a rotational change? And here in the setting, we kind of looked at different change point locations under the hypothesis. So there is no actual change, but the reason why I did that and looked at different change points anyway is because the other part of the data, so when I decrease the change point location to like 20% of the data, that means that I can only use 20% of the data to estimate my transformation, right? So I can use that to estimate the projection matrix P1 if I apply it to X2. So but one can see that actually works fine, and it might even be an improvement, because then we can base our test on a longer series, basically 80% of the data. But yeah, anyway, one can see it works. And here I did kind of like the sanity check. I applied the change point test by Han and Inouye to the first one where the change, to the first one, but there is no change, but with 0.5. So, and one can see that the change point test by Han and Inouye rejects, because what I did here is I modeled those data, or I simulated those data by implementing a rotational change. So for us, it's under the hypothesis, but for a regular change point like the one by Han and Inouye, it's under the alternative. So we actually get that the empirical rejection rate, or the rejection rate of the Han and Inouye test is like close to 1, because we have a rotational change. So for them, it's under the alternative, but for us, it's under the hypothesis. So moving on and away from the simulations, so that we don't have to look at tables anymore.
Can I just ask a question?
Yeah, of course.
Did you? I mean, I don't know how these how your loadings differed under the alternative.
Yeah.
But were there any structures that could be just driven by heteroscedasticity? I mean, but variance changes in the factors, and you eliminated those and pushed them in the loadings, as I understood. Or did I misunderstand something?
Okay, so you're saying when, so I mean, this is like observationally equivalent. So you're saying under the hypothesis or under the alternative?
Well, under the alternative, you have, I mean, if you have just a change in the variances of the loading, say, then I mean, you standardize your loadings in such a way that would be pushed into the loadings, right?
Yeah.
Sorry, the factors in the factors the factors have different variances. And were there any alternative hypotheses where your loadings just changed in that way? I mean, it's basically multiplying each column, I guess, by some number. Or did you have more complicated alternatives in mind, and when you checked your power and so on?
Okay, so I mean, that would for us be under the hypothesis what you were describing, right? When we have like only a multiplicative change by some like diagonal matrix or something in the factors, that would be still our hypothesis. But I mean, if I understood you correctly.
Oh, so your test is basically invariant to variance changes. If only the variance of the factors would change, then it would be
exactly, yeah. So that was like kind of the example I gave at the
I
beginning.
missed some of your transformations and somehow didn't interpret them.
Oh yeah, maybe I didn't clarify that.
No,
so
no,
that would maybe here. Sorry, I'm switching. Yeah, I mean, this is basically that we have this observational equivalence, right? So whether I look at this kind of hypothesis or I push the change basically into the factors, doesn't really matter. And I mean, I definitely checked like more complicated transformations, so it doesn't have to be just a diagonal or something. I mean, it's still it can just be any like non-singular matrix, and that is like for us the hypothesis. The alternative would be that only a partial set of, I don't know, like a partial set of the loadings changes, but the partial set of the colors.
Okay, thanks. That I guess I somehow didn't quite get all the transformations that you did and the way you identified basically your loadings that you were testing in a way. Okay, thanks very much.
Okay, yeah, thank you for the question. I mean, I didn't like go into too much detail about how I modeled the alternatives in the simulations, because okay, I guess like that would be a little bit too much maybe, but we looked at different alternatives, definitely we changed like only a partial set of the vectors, or all the vectors, and Yeah, so we basically got like decent results in all of those settings, and the power is like very similar to what one also gets in a regular change point test, where we only have the hypothesis that the lambdas are equal. Yeah, so just a little bit of a discussion maybe on our approach. So I gave this talk like at this time series conference in the NBIR conference this year, and the audience made this like suggestion to look at an alternative approach. So I said like we transform the data and artificially create a change point, right, under the alternative at least. So we create a time series which doesn't have a change under our hypothesis, but does have a change under the alternative. And this way we kind of know where the change occurs. However, maybe in order to improve the power of our test, an idea would be to still use a change point test, which doesn't just test at this time point t/2, but instead across a certain interval. So we would still take the supremum over our test statistic after calculating it for different points in time. And this is exactly the regular test Han and Inouye uses, because they assume they don't know the change, right? And we did that, and again, we kind of use this like pre and post break sample means. We compare them. We define this like wall type test statistic. We have this normalization through some long run variance matrix omega. And yeah, we can still show the convergence under the hypothesis, because as I said, our proofs very much rely on having consistent estimation of our transformed series for the factors. And then we can just apply the same techniques as in Han and Inouye. And again, they were looking at exactly this kind of test statistic, where they look at the supremum over a certain interval and calculate the test statistic for all those time points. And then one can see that it converges to this like process which depends on like independent Brownian motions. And we kind of use that as an alternative approach, and it turns out in some situations it can actually improve our test slightly. So that's kind of an interesting result, that the power can improve, but we don't really have like any structure when it does improve the test. So we looked at 2 data generating processes. So here for comparison, our results from the previous simulations. So the first one was like an additive change across a partial set of loadings, and the second one was a partial change in the loadings plus some rotational change. And we actually got in the previous test not very great results, or we didn't quite get to the power we would have liked. So, and we can see here that under this change, which basically only changes 20% of the entries of our loading matrix, the new approach also, or the alternative approach, also doesn't work very well. But here we got like some kind of improvement, which is quite nice, because that was the setting where we had like a rotational change, but only for like 3 out of 4 column vectors in the loadings. So this is just like a nice alternative approach, which might be interesting to explore a little bit more in simulations. Yeah, so with that, I move on to like a little bit of a discussion. So for the discussion part, I just want to remind people that this kind of problem is very much the question of whether the columns of a matrix lie in a subspace generated by the set of eigenvectors of another matrix. And this kind of problem has like a very long history. And I mean, Eaton and Tyler published this paper like in the early 90s, but that was like on a low dimensional setting, and they proposed a test statistic for that, and it works well. And yeah, it's a nice paper. But then people started asking this question, okay, what happens in the high dimensional setting? And yeah, natural thought is also to instead look at a comparison between both projection matrices. So one can also formulate that as basically comparing the projection matrix for one data set with the projection matrix of the other data set. And people were trying to push that to the high dimensional setting. And there are 2 interesting papers I want to point out here. So the first one is by Liao and Todorov, and they actually did something very similar to our paper. So they also studied the same problem, and they suggested a test statistic based on the Frobenius norm of the projection disparity between the pre and post-break loadings. So they actually did the comparison between the projections. But I want to point out that this kind of comparison pushes everything to the high-dimensional setting, right? Because the projection matrices are d-dimensional, or d times d. So whenever we are in a high-dimensional setting, this becomes technically much more complicated, because our approach still works in the lower dimensional setting where we do everything based on the factors, and the factors are actually lower dimensional objects, which makes everything much easier from a technical perspective, like in terms of proofs, for example. And also this kind of problem is very hard to like push this Eaton-Tyler paper to the high dimensional setting. And there's also like a recent work by Celine and Fun, who looked at the same thing, and they even like had to like introduce a new matrix norm, and they don't even get like any asymptotic distribution. So it's very hard to like show any asymptotic distribution for that. Instead, they have some finite sample properties and propose some bootstrap procedure. But that would also be maybe a nice comparison with our results. But yeah, to emphasize again, we kind of do everything like in the lower dimensional regime, because we managed to like reduce it to an analysis on the factors. Okay, so I will end my talk with the data application. Okay, before my conclusion at least. So for the data application, we looked at this like very classical Stock and Watson data set. So the original data set here is like 108 monthly and 79 quarterly time series. And it includes like, you know, prices, interest rates, stock prices, exchange rates, and so on. And as suggested in the paper by Stock and Watson, we removed some high-level aggregates, which are related by identities to lower-level aggregates, and we end up with this data set of 109 time series over a time of 190. So, and this data set has been like studied very extensively in the factor model literature, right? And over the last years, I would say the literature is kind of proposing that, you know, there are like two change points. And what we did is we based our analysis on this paper by Baltaghi, because as I said earlier, for our test, we kind of need to apply a regular change point test first. And since there was like some kind of, or has been some kind of agreement on there being two change points, or at least there's like a lot of evidence on that, we thought that's maybe a good paper to start with. So they find two change points, one in the 80s and one in the 90s. One in the 70s and one in the 80s. And they hypothesized for those two change points that the first break could be due to the impact of the Iranian Revolution on the oil price, and the second break could be due to the Great Moderation. So the corresponding estimates of the factors in the three regimes were 3, 3, and 4. And this is what we used as the basis for our test. So what we ended up doing is, for our results, we hypothesized that there is some kind of relationship between the loadings from the first regime and from the second regime, and then the second and the third. So, and we applied those tests. And again, for the second hypothesis, we kind of needed our test for changes in the loadings with different numbers of factors, because, okay, we have like 3 and 4. So we use this variation of our test. And our test actually rejects the first hypothesis, but it does not reject the second hypothesis. So, and as an interpretation, going back to what Baltaghi hypothesized in terms of interpretation, they said that the second break might be due to the Great Moderation. So, and the Great Moderation refers to a period of decreased macroeconomic volatility. So, for example, in the United States, that started in the 1980s, and then one could observe that the standard deviation of the quarterly GDP declined by half, and the standard deviation of inflation declined by 2/3, and so on. So there was like a lot of decline in volatility, and that our test doesn't reject this hypothesis might maybe, I mean, this is like all kind of hypothesizing here, but maybe indicate that there was like somehow a more structured change happening, so that actually just the that the changes in volatility occurred in a more structured way, that there is some kind of transformation in the loadings, instead of having a change which says that there's no relationship between the loadings. Or one can also explain it in terms of the volatility, as I said earlier. Yeah, but I mean, this is like always hard to interpret those things, and obviously they're it's questionable. But yeah, so with that, concluding, to summarize our results, so we proposed this hypothesis test, which was motivated by learning relationships across different individuals, but also by structural changes in one data set or in one factor model. So, and we try to discover whether structural changes between two models are due to linear transformations. So for testing for structural changes in high-dimensional factor models, our test allowed us to further characterize what kind of change occurs. And for that, we kind of developed this new hypothesis test, and its theoretical investigation was basically to show that we have some convergence under the hypothesis, and also to investigate what happens under the alternative. So the nice thing here is that we avoided doing any like rank test, because that would be an alternative approach maybe. And then also we kind of operate on a lower dimensional space. So we didn't need to do anything like in a high dimensional setting where we compare projection matrices. So we did everything based on the factors. We had like some new findings on the Stock and Watson data set. Yeah, and to end this, we can also think about some related future work. So one would definitely be to push everything to like having more than just two subjects, which is interesting, for example, in those settings I mentioned at the beginning, like in neuroscience or something, you would like to compare not just two subjects, but you usually have like a group of subjects. So there's like kind of the question of how to do that in a reasonable way, since we have to like transform every single series. So then there is this partial testing, since our test like very much relies on those projection matrices and the observational equivalence to changes in volatility. The question is, okay, can we still find a way of doing partial testing based on the factors? And by partial testing, I mean finding like out whether there are changes in the loadings, but only in a subset of column vectors. But I think that seems very hard to reduce that to changes on the factors. And there's always like, so on the volatility of the factors, and there's always this question of like, well, how do I have to do any like sequential testing? Do I want to figure out which columns are actually shared and so on? So there are a lot of questions regarding that. And yeah, so and then there's definitely the question of investigating other change point tests, because I think over the last 10 years since the publication of Han and Inouye, people have been like comparing other tests to the Han and Inouye test and definitely found like improvements. So it would be possible to use other change point tests, right, and investigate our transformed series based on different change point tests. Yeah, and that's the end of my talk. Thank you.
Perfect. Thank you so much, Marie. That was a wonderful talk. So I'm just going to stop the recording.